Thank you very much. I'm actually presenting on behalf of three of my colleagues. My name is Brendan Hausberger, Bilal Patel, who's the lead researcher in this field, Diane Hildebrandt and David Glass, who you saw earlier in the session. What we're presenting here is the result of, and I'm taking a total opposite approach to what's been taken by a lot of the researchers who presented their work here today. We're working from the outside in. So instead of saying what is the catalyst doing, we're trying to say where should we be operating, where should we be looking at developing our catalyst to operate. So a little bit of a backwards approach, and forgive me if I seem a little bit out of place among some of the presentations we've seen today. What we've been working on for approximately the last 10 to 15 years is developing a set of methodologies that allow us to actually take a chemical process, take into account the economic pressures that we do face as well as the environmental pressures, and try and assess a systematic methodology for the design and construction of these processes as we move forward. As a result of this, we've come with a set of tools which allow us to actually target these processes and identify what the key inefficiencies are from a systematic design perspective, and try and identify what the opportunities are that exist if we were to make alterations to how we operate and design these processes. We call this methodology complete process synthesis, which just happens to correspond to the name of our center. And what we essentially aim to do is set fundamental performance targets for our process. These vary. For hydrocarbon-based processes, we look at CO2 emissions, as well as looking at the overall carbon efficiency. One can call it almost wheel-to-well type efficiencies. How efficiently do we turn the carbon in our feedstocks into the fuel chemicals that we spit out at the back end of our process? We try to develop these methods in such a way that they don't rely upon a large amount of data and a large amount of information, because often when we're starting the earlier stages of design, which is when we set the key aspects of our process, by the decisions we take, we don't have that information available. We don't have the luxury of 12 months or a year's laboratory work. We're really working blind to some extent, and on the data we can find on the web, Perry, or what other people have very generously published. We also take a look at the entire process from a systematic approach, as opposed to looking at the technologies that are applied in various sections of it. So you'll see that the observations we make are not dependent upon the technology or the flow sheet equipment that one has selected, but rather look at the overall process. They give us insights into the process both from a resource utilization and integration perspective, and the very same tools that we apply at this very high level can be reapplied at the very detailed level from an equipment perspective to get us more information. So, what do we need to do this, and why do we need to do this? Well, if you don't know what your process is capable of, how do you assess the various technologies which are on the table? We've seen today presentations of various parties who are giving us very different operating regions and very different results for catalysts. How do we know which is the best one for our process? How do we assess that information? We believe that a tool such as ours gives us some ability to do that. These targets give us the limits of performance for our overall process, and they allow us to determine a target without intrinsic knowledge of the flow sheet. That information gives us certain insights into the process. They talk about our process efficiency, where we have structural reversibilities, and as a result of this, we're able to actually develop and synthesize a flow sheet, as well as understand what price we're paying as we synthesize our flow sheet and make certain decisions in that. So, we have three tools we make use of for doing this. The first one is the fundamental mass balance, which you're all familiar with from days of yore. We then go to an energy balance perspective and an entropy balance. And what we'll show in the course of this presentation is that each one of those particular setups gives us a certain set of limitations and constraints on how we operate and design our process. And some of these kick in and some of them don't. Overall, this gives us an overall methodology that we can work forward with. So, if we take CO2 as our control variable here, for any hydrocarbon-based process, be it CTL, GTL, or BTL, or BTM, or any one of the other three-letter acronyms you choose to play with, we've got a process that essentially takes some feedstock, turns it into some products, and along the way emits some CO2 or other byproducts or harmful emissions. So the question we pose when we're looking at CTL or GTL is, what is the minimum amount of CO2 we can produce per mole of product that we spit out of the process? I mentioned that this is an integration of processes, and the process we're going to be integrating in this particular presentation is that of methanol production and CTL technology or GTL technology. Methanol is a nice fuel. It's being proposed as being used for fuel cells as well as being used directly as a transportation fuel, either as methanol or being converted to DME. It also is a useful fuel for developing economies, in that it's a nice building block that can be used for higher value chemical processes down the line, which opens up a new set of opportunities. Currently, methanol is largely produced either by natural gas or coal feedstocks if we're going to look at a CTM or a BTM type process. So let's take a look at the standard typical methanol process to try and get some insights into this. What I'm trying to show you here are some of the results of our methodologies, and I'm not going into the detail of the methodologies, that would take too long and wouldn't add that much value. There are two fundamental processes that we can make use of, or that are currently made use of for production of methanol. The one is using a partial oxidative formation of methane and going across the methanol process. It looks very nice. Here's the standard process mass balance we've got. The second one is looking at a steam reforming based technology for our methane feedstocks, and in this case we have, if we look at the overall balances on it, the production of a hydrogen byproduct on the overall process. Again, bear in mind that what I'm talking about here is not necessarily the chemistry of the reaction that takes place, but the overall process chemistry that we'd be considering. If we consider these in a little bit more detail and go into the thermodynamics of the process, this is what we find. We're talking here about the standard change in enthalpy of the process and the standard change in Gibbs free energy of the process. So taking a look at the first process, which is the partial oxidative one, this looks very, very positive from a process perspective. The first thing is it's exothermic, so it acts as a heat producer, which is always a positive state to be worked in for designing a process. And the second thing is it's a work producer. Why that's important may not necessarily be that relevant to us, other than if you go back to second or third year chemistry, you'll recall that if the delta G is negative, it means the process proceeds to some noticeable extent without adding any extra work or energy to it. You'll find out later, if we look at these things, that it becomes a lot more important to us, because if our process is not actually a work producer, we end up having to put work in either by separation or compression at some point in the design of our process. So it's a feasible process, and this would make it a good target for us to work towards. There's one little sticking point that we run into. There's unfortunately no commercial catalyst that allows us to do the partial oxidation of methane directly to methanol. Very nice if there was, but there isn't. So if we take a look at the second process, we find that this process is undesirable for two extents. The first of all, it's endothermic, so we do need to put heat into our process. And the second one is it does require work input. How do we supply the energy that we require? Well, in principle, it's possible that we can take that excess hydrogen that we provide and we can combust it. So here we go, a very simple process. Separation of hydrogen and methanol is a fairly standard and simple process. One is almost incondensable, the other one condenses fairly readily. We take out our hydrogen, we combust it. Turns out we produce excess heat, and we can put heat back into our process and we make water. Now, any of you who have anything to do with designing a process will take one look at that and go, hang on a second, you're being stupid, you're wasting an opportunity, you're putting water in, you're taking water out, mass integrate it, put it back in. So we can return it to the process, it's called mass integration. And the interesting thing to note about this is what we've done is we've taken a chemistry which looked to be undesirable in the form of the fact that it was methane and oxygen. We said there was no way of implementing it. And by merely adopting current technology which does work and doing some mass integration, we've turned that into an overall process chemistry that is much more favorable. Because that chemistry with the recycling the water internally is exactly the same as the chemistry and the overall process thermodynamics that we got from the partial oxidation of methane to methanol. Now, any one of you who's a smart engineer would have been able to arrive at that result, because in this case it's a fairly simple process, it's very easy to see. What we've developed is a methodology that systematically allows us to give rise to these results even in more complicated situations. So, by mass and heat integration, we make a non-feasible process feasible by what we're able to do to break it into two processes, and we're able to achieve the mass and energy targets by putting this implementation into place. So, we've got a new and more systematic method of doing this and getting to results and approaching this. We apply mass, energy, and work balances or entropy balances to achieve this, and I'm not going to go into the detail of those. That's one of the courses we run as we part here. If we take a look at a coal to liquids process in isolation as well, the first thing we need to identify is that any process has certain limiting mass, energy, and entropy balances. These establish targets for our process on which our process can operate. In every single case, and it generally turns out one of these is limiting and the others are non-limiting, which give you some degrees of freedom. That limiting process becomes the global target that we should be designing our processes for. Applying these allows us to understand what limits our process efficiency and how we can improve upon it. So, take an overall coal to liquids process that produces 1 mole, and we're modeling our CTL products as CH2 as methyl groups. It turns out from a thermodynamics perspective, this is a nice approximation that works across the entire range of numbers for a CTL. So writing a generic model where we have W as a stoichiometric coefficient for coal, X for water, Y for oxygen, we produce 1 mole of hydrocarbons and Z of CO2. We can draw a process block diagram that looks somewhat like this. And what we can then do is actually solve for the coefficients W, X, Y, and Z when we apply a mass balance on carbon, hydrogen, and oxygen. In addition, what we can do is apply the energy balance on the overall process, which gives us another parameter. We've got 3 equations here, 4 unknowns. By adding our energy balance in, we're able to get the fourth unknown found, and we've now got a defined process. And previous work we've done in a group has shown that the coal to liquids process is actually limited by the energy balance, and our highest carbon efficiency comes about when we're not producing excess heat from our process. Not scarcely surprising, seeing as Fischer-Tropsch is an exothermic process. So any extra heat we throw out over and above what we absolutely have to throw out in our process means we've burnt coal that we didn't need to burn in our process overall. So this gives us a target to work towards. So that target, when we solve the equation for our overall balance, gives us the following. And you'll see what this tells us here is that water and oxygen are primarily feedstocks for our process. We have to make CO2 as a product. We get a carbon efficiency on a CTL process on its own that sits at about 61%. Now, there is no CTL process in the world that currently can boast an overall carbon efficiency of 61%. Why? Well, this is working on thermodynamic optima. We're assuming reversibility here, which obviously is not actually feasibly attainable in real life. And ideally, the limit we can get to is the fact that per ton of CH2s that we produce, we will be spitting out a minimum of 2.03 tons of CO2 as waste material. Is there any way we can improve this process because this is a fundamental thermodynamic limitation. So we can't do any better by doing better equipment. It doesn't matter what flow sheet you put in, it doesn't matter how fancy your catalyst is, you're not going to be able to beat this rule because this is defined by the overall rules of thermodynamics on the overall process. What if we take a look at the combination of producing methanol and liquid fuels in the same process? And look at determining some targets for the co-production of methanol and CH2. We go about this by writing an overall balance. So we've got our coal, we've got our methane or natural gas, we've got water, oxygen, CO2, and we write F as being the fraction of CH2s that we make relative to the fraction of methanols that we make. And we can solve this balance using the same energy, mass, and work balances that we had before, and we can get to a set of equations. So, the 3 balances we consider are the mass balance, and the mass target balance we're going to set on is working on our CO2 emissions. We can look at the energy balance in terms of the enthalpy of our process, and the work or entropy balance look at the delta G of our overall process. Now, these numbers and equations become very messy, so I'm going to present the next set of results, a set of graphical techniques and graphical results that come out. And what we're going to plot, and this is a linear programming based approach, the x-axis here that you can't see is the methanol moles, methane moles, that we would make use of, and the vertical axis is the coal moles. And what we've plotted here is ISO CO2 production curves. On the left hand, on the lower side of the zero curve, what you'll see, and you can't see these unfortunately are shaded regions, I'm just going to actually page up there. Below this curve, what happens is we actually feed CO2 into the process. So below this curve, if we're operating in a regime where, for example, we've got 0.5 moles of methane and we have 0.1 mole of coal, we would then end up producing 0.4, we would end up consuming 0.4 moles of CO2 in our process. Right? And that comes about from the thermodynamics of our process. The technology to actually implement this is not what we're stating. We're merely stating that using a feedstock of those 2 combinations to produce 1 mole split in a various ratio between the CH2s and the methane would allow you to actually consume CO2. On the other hand, if we were operating above this curve, we'd actually make CO2 as one of the products. Right? And this is working again from a fundamental perspective. Now, no one, I think, in the room would ever think of using CTL in a process that actually consumes CO2, which is why we're looking at sequestration. If we take a look at oxygen, we can plot an equivalent set of curves, and apologies for the colors here, but you can actually see the curves have got the same slope, and they actually lie across like here. In this particular case, what we've got is oxygen feed on the right-hand side, so operating in this region we need to add oxygen, and operating on the opposite side, there's actually the possibility from a thermodynamics perspective of producing oxygen coming out of our process. Probably not a particularly desirable state to work in, because why do we want to do that? It means we end up doing a lot of separation that we would prefer not to do. So, we've now got targets for the flow of carbon monoxide, oxygen, and water. We can determine feasible regions, and we can scan all the options from a flow sheet perspective of combining methane and coal to produce products, and try and identify ones that will meet a certain target. In principle, what we can do is, and what the result of this says, is that in principle we can design processes that not only consume CO2, but can do so without any oxygen feed addition, which is quite an interesting principle to look at. So, if we were to set as our target having no CO2 in and using no oxygen as a feedstock to our process. Why do we pick these as targets? Well, we all know that we don't want to be spitting CO2 out because we have to do something to solve that problem somewhere up or down the line, sequestration or otherwise. Not making use of oxygen into our process has a massive capital effect on our plants, because reducing the oxygen consumption of our plants could mean possibly the elimination of an air separation unit, which, working in this field, you will know is a massive energy consumer and adds inherently to the CO2 emissions for our process in generating the electricity or power to run that. If we look at that, the solution that comes out of our graph tells us this. We need to use half our feedstock as natural gas, half our feedstock is coal, we put an equivalent amount of water, and we're able to produce methanol and CH2s in equal amounts. That's very pretty. It tells us that it is possible to do this. Can we actually achieve this, and how do we go about it? So let's go back to that methanol process we take a look at. You'll recall in the methanol process, we looked at the steam reforming of methane, it took us to methanol, and there's an intermediate step as well that takes us to methanol and hydrogen. So from a flow sheeting perspective, this is what we start off with. We take half our mole of methane and half our mole of water, we put them in together, and we produce half a mole of hydrogen and half a mole of methanol. That hydrogen we take, we combine it as a feedstock into a process that has coal as a feed process to it, and we produce our half a mole of FT products coming out. Overall, if we look at that process, what we end up is the balance that we've got otherwise. So now we've been able to translate the results of our assessment into a flow sheet, albeit on a block flow sheet perspective at this point in time. We did say that we'd have to take a look at the work and energy as well. What we've plotted on this curve is the F factor. Remember, the F was the ratio of a fraction of products which were being taken out as FT products relative to the amount of methanol we were taking. So in this case, for the plot we've shown here, we've got half-half, which is our product. The black curve here represents delta G equals 0, so that's when our process is work neutral. We're not having to put extra compression work in, and we're not recovering any compression work out of it, which is a good thing, because if you look at Fischer-Tropsch, we actually end up reducing the number of moles over the reaction, as do we in methanol. If we take a look at the delta H, this is when we're not putting work into our process and we're not taking work out, you'll see it lies below. On the left-hand side, the consequence of this would be that our delta H would be greater than 0, it's endothermic, the overall process, we need to find a heat source and put it in. On the right-hand side, we've got delta H is less than 0, which means it becomes exothermic and it's ejecting heat. Likewise, we can similarly show for delta G on the two sides of the curves. Below the curve, delta G is greater than 0, means to put work in, and on this side we can extract work from our process. And again, these are plotted on coal versus methane. Apologies, we just can't see the methane curve at the bottom here. So if we zoom in, and what we've plotted here is the extreme cases. So in this case, 1, it's a pure FD process, and in the 0 case, we're looking at a pure methanol process, and we've shown the half process in the middle. The same curves correspond. We notice if we look at the high methane end, or the high methane feedstock end, the limiting characteristic in every case, whether we're looking at pure methanol, whether we're looking at a half and half product spectrum, or if we're looking at a pure FT process spectrum, we're always limited by the delta G. We end up in a situation where we need to put work into our process. If we look on the other end with the coal process, we find our coal process are limited by delta H, and that's always the limiting factor here. So heat predominates, the heat flows in and out of our process dominates in coal to liquids, and in gas to liquid type processes, we find it's the work process that dominates. So let's put this all together now. So what I've done here is I've taken those three plots, I've put them together. So we've got our CO2 profile sitting on here, we've got our oxygen profile sitting on here, and we've got our delta G's and our delta H's. We need to zoom in because otherwise it becomes a very complicated mess that no one can read anything from. If we take a look at the process here, we're limited on the lower boundary in terms of the feasible regions by the delta G, because if we operate on this side of the delta G curve, it means we need to do work in our process and put work into our process, something which is undesirable and difficult to do. On this side, we're limited by our CO2 emissions. Moving above this point means we start to emit CO2, and below this point, we're actually consuming CO2. And as a result, we're able to define a feasible region. These are actually colored. Unfortunately, you can't see the coloring. The region is actually bounded on this side by the black curve up to the apex, and from there it's bounded on that side. You'll recall what we were talking about was a half and half mixture of methane and CO2. So we take that up. Half and half actually puts us in a region up here where we're emitting CO2, and in addition, we're actually being required to add work in. So our initial solution, where we looked at half and half, doesn't actually work when we consider the work and energy processes. So we need to look at another solution, and it turns out for our product where we make half methanol and we make half FT products, the limiting case for that turns out to be this point here. To try and reduce those to words and numbers, make it easier to understand. Both delta G and delta H are positive when we looked at the half and half product we looked at earlier, which means we need to feed in oxygen to make the process feasible. Well, duh, we all know CTL, GTL don't work unless you put an energy, some way of making energy, and you need to combust either the coal or the methane to do that. So the limiting process we end up from an overall case perspective is the following one. We have approximately 64% methane or natural gas, 36% coal as our feedstock. We introduce water into it and oxygen, and we produce as a product our methanol and our CH2s. You'll notice that the net process overall here doesn't actually emit any CO2, and likewise we don't have to put any work from a compression perspective into this or a separation perspective. We also have an overall production of heat from our process, which means we can use this as a heat source for other processes externally, or we can throw it away. So, what does the flow sheet look like that we develop out of this? Well, here we take our methanol production process, we take our half a mole of methane coming in, and our half a mole of water coming in. We take the hydrogen off that, we combust a portion of that to produce the energy that we require, and that produces water which feeds into our process. We're allowed to recycle that water back into our methanol production, and that gives us a feedstock there. Another amount of the hydrogen that we take out actually gets recycled around into our CH2 production. It gets combined with some of the methane from our CH2 from our feedstock, and some of the coal from our process, produce half a mole of CH2. So overall, you'll notice we've gone back to a chemistry that takes half a mole of methane, and it takes 0.36. It's half a mole plus that, so that's your 0.64 of methane, 0.36 of coal to produce half methanol, and half a mole of CH2 products. And of course, we also inject excess heat out of this process. So what have we got here? And I've gone fairly rapidly through the application of a series of different tools. I'm not going to detail those, as I say, we do at the AICHE, amongst other things, run a course on how the tools actually get to these results. I'm really presenting the results of the tools. We've got a simple set of systematic tools that can actually allow you to assess what the overall process optimal is and to screen various processes. We then use mass energy and Gibbs energy balances to allow us to come up with a set of limiting criteria in our process. They identify what the limiting variables for any particular flow sheet or overall process are, and allow us to determine what a feasible operating range is. Once we've got that feasible operating range, we can then go to the laboratory and start to assess our processes and the intrinsic equipment that we plan to use and how well it actually works within that range of conditions. Obviously, we find ourselves in certain cases in a situation where we can't operate, and we may have to move into a delta G being positive regime and start looking at compression on our process or alternatively other separation methodologies. But now we understand why we're moving to those regimes as opposed to merely designing and incrementally improving on existing designs for such processes. We've also taken a look at the co-production of two products, in this case methanol and FT, for coal and or methane processes, and we've shown how we can, in principle, achieve zero CO2 processes for these. And we've taken a look at how we synthesize a flow sheet as a result of these. That's a very quick thumbnail of the results we've got. The first question which is sure to be thrown at me is, well, that's very nice, but in theory, how did it actually really work? The core concepts that we've actually integrated in this, and to give you an idea of how long it takes to do an assessment like this, the core calculation for this particular presentation was done in a morning on a basis of information that's pulled out of a Perry set of tables. Of course, it didn't take a morning to figure out how to do it. That's always the result. It's a bit like some of the numerical optimization people who present who tell you it took 30 seconds to work out how to solve a problem. Yeah, it took 30 seconds, but it took 3 weeks to set up the formulation. The methodologies here are a result of 5 or 6 years of research work in the sector. The results of this are actually what we're making use of. David Glasser referred earlier to the fact that we're in the process of developing a CTL process in Australia and China. This methodology is actually what's being used in developing the experimental laboratory program for those particular processes. Interestingly enough, it's given us a lot of insights into the process and led to some fairly novel innovations in the overall design of the process, and is looking right now at some significant reductions in the CO2, even without considering new chemistries or new processes. Merely by taking existing off-the-shelf catalysts, taking existing off-the-shelf gasifiers and reformers, we're able to achieve significant improvements over what other technologies can offer right now. So So that being all said and done, if there's any questions, I'd be welcome to entertain them.
Any questions?
Your point is well taken, and obviously some level of pre-optimization is a good thing to do. Use a very good example, sort of a 2 or 3 dimensional space that we could visualize. Now when you go to a much larger dimensional space, let me backtrack here. We benefited from the fact that you had knowledge of 3 or 4 chemistries that would complement each other nicely. How do we expand this in a huge dimensional space to sort of figure out what chemistries we should get to complement with each other?
Certainly, I mean, it's a very valid point. How we expand this is twofold. The one thing is that it's based on a linear programming methodology. So linear programming in as high dimension as you want is a fairly established science. So there's no fundamental difficulty in looking at much higher dimensional issues from that perspective. The one thing that we are identifying out of this is that there has to be an overlap in terms of the base product family that you're looking at. So I would be the last one to suggest moving significantly outside of petrochemical. If you're looking at petrochemical, you're looking at petrochemical spectrum. Where there are natural synergies is then one way one would look outside of that. So for example, one of the other examples we've been looking at is ammonia, bringing ammonia on board. If you know you have to make oxygen, you know you've got a nitrogen byproduct. So start to look at the nitrogen family of products. The beauty of this process is that once you, and we've done similar examples with biochemicals where it gets a lot more complicated very rapidly. Once you have your set of core elements, one could theoretically, and we haven't done this, although we did something similar, as I say, in the biomedical examples, take the entire family of components that could be made. So for example, you've got carbon, nitrogen, oxygen, hydrogen. There's a set of families of chemicals out of that have commercial value. Take a look at those and see what you can do with them. So my answer to you would be simply take the base elements that you're working with, take a look at the commercial products of value to yourself or perceived value to you and your company are, and put those in and see where the combinations arise. The interesting thing is if you start looking at ammonia, methanol, and FT together, you end up getting told that you only want to use 2 of them, not all 3 together. So this is not a generic solution which tells you always, well, you want a combination of all. The other beauty that comes out of this is the fact that we've obviously worked purely on a very scientific, clean, clinical, academic perspective and not considering the economics in it. But once one has the mass balanced targets, there'd be no difficulty in converting that into an economic target and translating it from that perspective. And it doesn't complicate the solution or the methodology in any way.
So whereas in refinery LPs, they limit themselves by knowledge of what the processes are and what those chemistries are, you would limit yourself by, if you will, what the chemistries of interest are.
Precisely. And what I'd even go further to do is to say the fact that the other key element that comes out of this, which I think is novel, is the fact that by not considering the process equipment, we get ourselves away from the mindset of, well, I don't have a piece of equipment that can do partial oxidation. It says, what if I could do partial oxidation, what is it? Where does the benefit derive from that? Well, once I know what my carbon efficiencies are from a process that can do that, I have a direct metric that can be measured against my best available technology right now on the market. If the differential between those is 5%, then investing in a brand new technology probably doesn't make sense. Although it may if you look at a high specialty chemical. If, however, the difference is 75%, then there's a case to be made to the financial decision makers in my company to say, hold a second, there's somewhere to go with this. And it's not purely a pie in the sky thing, which has always been very difficult up until now. The other nice thing about this, which we've particularly taken advantage of, is that we can assume that if you're combining technology in a various way, the inefficiency or efficiency of your current, of the process equipment you can design is not going to be fundamentally different to what else is on the market. So if I take how can you put a rose-tinted glasses view of the current technology and measure its carbon efficiencies, and I take a rose-tinted view of my new conceptual technologies, I actually have a fair basis of comparison between those two. We can also reapply these, and this is the part that we haven't presented because sort of our proprietary information and what we're using for our consulting side and our project development side, is that once you've applied this on this very gross genetic scale, you can then go back and look at specific items of equipment and start to build in real inefficiencies and start to get some very interesting results out of those. You start to understand that what people think are the limiting factors, these processes in fact are not necessarily the limiting processes at all.
I have a simple question. When you were showing the graphs of the
How did you calculate the mole numbers of coal? Did you assume, did you use molecular weight of coal or just assume carbon?
At this point in time, all of the tons we refer to are ash-free coal. So it's a carbon basis. We have done an example where we took a specific carbon composition, which had a carbon-hydrogen ratio in it, and worked on that. So you can make whatever basis you need. For these calculations, however, it was ash-free carbon. So it was
What if the coal is lower-end coal and has lots of oxygen? How is it going to impact your?
It will change things significantly because of the fact that you've now got additional oxygen sources in your process.
So can you put into your calculation?
It's not an issue because, no, you can quite easily, because as long as you have a composition or representative analysis of that coal, and you can characterize how much oxygenates there are there, or what the oxygen content is, one can then take account of that in your mass balances and your energy balances as well.
Any question? All right, let's thank again. I believe the last paper will not be presented. I got an email from the author that he was going to send someone to present his paper, but nobody has showed up to present the paper. I assume that this is going to be the end of the session. Thank you very much for coming. Bert and I appreciate your contribution. And the session will continue tomorrow morning at 8 o'clock.
8:30. 8:30. 8:30.
Oh, I'm sorry, 8:30.
Thank you. Little more rest.
Yes, please come back and meet here. It's going to be in the same room.
Thank you.
Thank you very much.